This is the solution for the mock for integration. You are asked to calculate the amount of paint necessary to paint the side of a new high-speed rail train. The rectangular part of the train is 3.5 meters high, and the curved portion is modeled with the function y equals 3 log x plus 0.5. The area between the x-axis and the piecewise function below indicates the area to be painted. So just to make it clear what part we're painting, I am going to try to paint it with my highlighter. So basically, we want to find this area here. And they're going to walk us through it, so don't worry. The first step says find the x-intercept of the curve. And it turns out that the x-intercept of the curved part, this is the curved part, right? And this is the horizontal line part. So the x-intercept of the curve is this part I've circled right here. Whenever you find an x-intercept, it's the same in our class because we always use a calculator no matter what function it is. So I'm just going to put the curve function, which turns out to be y equals 3 log x plus 0.5. They put it in two places. They put it in the text of the problem and they put it here on the picture, so it's pretty hard to miss. So I'm going to type that into the calculator. 3 log x, don't panic that it's a log, all we do is type it in, plus 0.5. And I'm going to graph it. And here's my graph. And you can see that the graph here cuts it off here because we're only looking at the top half of the graph. So we want to know what this x-intercept is. We need to use a calc function to do that. Let's see if we can remember which it is. Second calc, which one detects when the height is 0 or the x-intercept? Yeah, second calc 0. So we go to second calc 0. And then the left bound of the function. Now one thing, don't panic when you don't see the cursor here, because when you have log, the cursor starts out in the very middle. And the very middle for log is at negative infinity. So the first thing you need to do with log is you need to use the right arrow to make the cursor appear on the screen, okay? That's the first thing you want to do with log. So the left bound, I just need to put it slightly to the left of the x-intercept right there. So I'm just going to hit enter since the cursor is on the screen. And then I go slightly to the right. And then I hit enter. And then I hit guess. Doesn't matter where you hit guess. And the answer is 0.681, 0. So the x-intercept is 0.681. If you give it in coordinates like 0.681, 0, that's fine too. But that's fine. Hence, write down the integral expression of the area between the x-axis and the curved portion of the train's profile shown. So, so we're just looking for the x-axis and the curved portion right now. So that would be just this part here, okay? Which means that we're going to go from this point, we're going to scan from this left limit to this right limit of 10, okay? So remember, when you write an integral function, here you need to put the limits, here you need to put the function, and then you end the sentence with dx, okay? Because the x-axis is called x. So the left limit you put down here, and that would be 0.681 according to part A. And then the right limit would be 10, because that's where the curved portion ends. And then in the middle, you're going to put the function itself, which is 3 log x plus 0.5. The answer for B already. Okay, let's go to the next one. Oops. C. Hence, find the total area of the side of the train to be painted. So in this particular case, we need to find the yellow part, and then after that, we need to find the rectangular part next to it, which I'm going to highlight blue. Okay, and so let's find the yellow part first because we already have the expression here. Let's put that in the calculator, okay? The yellow part. So what we're going to do is, since we already have it in y equals, it's easier just to use y equals, but I'll show you how to do it the other way right after this. So I'm just going to do second calc integral number 7. And the function's already in there, so now I just need to put in the limits of 0.681 and 10. First, it asks for the lower limit, which is 0.681. And then I put the upper limit, which is 10. And then it colors in this yellow part here, okay? And the answer, it says, is 22.9. So, oops, the yellow part is 22.9. And then I'm going to add it to the blue part, which, let's see, the blue part we can calculate using integrals or just with length times width. So length times width, there's 5 units across, right? And there's 3.5 units tall. So if we were just going to do this with length times width, we would do 3.5 times 5, which is 17.5. We could do that with an integral too, and I'll show you how to do that in just a second, okay? So let's do this integral using an alternative method, which is the math key. If you go into the math key, do you see there's something called function integral, number 9? So if we go into function integral, we can just type everything in here. And this might look like it's a lot easier, and I think it is in many cases. The only problem with this one is it doesn't check your work in any way, right? So if you type the wrong thing in, you're not going to know that your answer is totally wrong. And when you use the graphing method, look, be careful, because there's always an extra set of parentheses out here. So I need to close that parentheses to put plus 0.5, right? Okay, and then I need to put my dx here. And then I hit enter. And then I'll also get 22.9, right? And then the 22.9 is the yellow section, and then I need to figure out the blue section too. I could figure out the blue section using integrals also. So let me just show you how to do that. 9, and then in this case, I'm going to scan from the left limit of 10, the right limit of 15. So like I was saying, if you use the other method where it graphs, it colors in and draws a picture, kind of like the one we already have on our paper. And then it makes it easier to figure out if you did the right thing. Okay, and this function here, and this is maybe the challenging part of it, this function of the horizontal line is y equals 3.5, because we know the height of the flat part of the train is 3.5 meters tall. So y equals 3.5 is the equation we put inside the function. And then we put an x here. And then that gives us 17.5, just like we calculated with length times width. Okay, and so what is 17.5 plus 22.85? It's 40.4. So that's the area of the side of the train. Okay, all right, that's it for number 1. Let's go to number 2. Number 2, the derivative of the function f is given by f dash equals 3/2 x squared plus x plus 3. Find all possible functions of f of x. So let's set aside all possible for a while, and let's just go and try to find the antiderivative of f dash, because basically if they're saying find the function f, when they give us f dash, they want us to take the antiderivative of the derivative, right? So remember, the antiderivative is the same thing as the integral. So let's find the integral of this, shall we? So 3/2 x squared, basically the way you find the integral of that is you set aside the coefficient 3/2, and then you take the x squared and you make that into x with one additional number in the power. So x squared becomes x cubed, and then you divide by 3. When you find the integral of x, it would just be x to the first, and so you change that to x squared, and then you divide by the 2. And there's no coefficient, so you just leave that there. Finally, the integral of 3 would be 3x. And then finally, whenever you take an integral, you need to add a plus capital C. which is the integration constant, which we might find later. And then if you are wondering, why are they saying all possible functions f of x? It's because when we find this function, the c value, so if we put plus capital C there, and by the way, c is like any real number, then that means that this could be any number of an infinite number of functions, right? Just one thing, we need to simplify this because this, 3 halves divided by 3 is not complete yet. So you could do 3 halves divided by 3 in the calculator, and that will give you 0.5. Or you cancel out the 3's, and that'll give you 1/2. Either way is fine. So there's my answer. 1/2 x cubed plus x squared over 2 plus 3x plus c. Okay? Then it says, the curve y equals f of x passes through the point -1, 2. Find this specific function f of x. Okay, so in this case, they're giving us values for x and y, which define exactly which function x we're talking about. Like before, we were saying, oh, it could be any number one, any of these infinite functions plus capital C. Now we're going to be able to figure out what capital C is. So let's do that. So what we're going to do is we're going to say, okay, they're giving us an x value and they're giving us a y value that goes with it. If I substitute those in here, and remember f of x is the same thing as y, so I could put, on the left side, I'm going to put 2, and on the right side, I'm going to substitute in -1 whenever I see x. And I see it 3 times, don't I? And then I leave the capital C there. Now I'm going to solve for the capital C. So 2, and then you could do a lot of this in the calculator. Why don't we do this in the calculator? Be really careful that whenever you substitute in for x, you put parentheses around it, and then you can't go wrong. So I'm going to put, first I'm going to put 1/2, oops. First I'm going to put 1/2, and then I'm going to put -1, make sure you use this negative here, cubed, plus -1 squared divided by 2 plus 3 times -1. And I can't simplify the c, so I'm just going to, so that'll give me -3 plus c. So c is equal to, and now I just add 3 to both sides, and that'll give me, oops, there's some lag here. Oh my gosh, come on, eraser. There's so much lag here. Good thing I'm not playing a video game. Plus 3. And capital C equal to 5. So if I wanted to rewrite the function, I could plug in the C, take out my y and x. So I'm going to put f of x, so much lag. And this is like a better computer than I usually use. 1/2 x cubed plus x squared over 2 plus 3x plus 5. And now I'm done. That is the function. I can't even like, the computer is so laggy, I can't even like scroll this thing up. Oh, there we go. Thank you. All right, that's it. Really quick, huh?